Okay, Russ, if you could take us to the next slide. So just making sure that everybody's found themselves in the right place. Today, our course is going to be diagnosing heating and cooling problems in the home with our instructor, Russ King from Coded Energy. Next slide, please. So everybody knows how to use Zoom at this point, but just a little bit of how we tend to run things. If you have any questions for Russ as he's going along, please put them in the chat, and I will be sure to get Russ's attention when appropriate and ask that question on your behalf. So there will be time for questions throughout. Just please keep them in the chat. Next slide. So before we dive in, I'll tell you a little bit about Tri-County Regional Energy Network, who is sponsoring this course today. My name is Greg Godero with 3C Ren. I'm one of our program managers. So if you need any assistance today, feel free to message me directly. 3C Ren serves San Luis Obispo, Santa Barbara, and Ventura counties, offering services for building professionals and households. And we're funded by ratepayer dollars, which is a small tax on all utility bills, energy utility bills. Next slide, please. So I'm going to be the staff online today. So again, feel free to get in touch with me if you need anything. Next. And then briefly, I'm going to tell you just about our 3 programs today. Next. So the first program we have is Energy Code Connect. We serve all building professionals with our Energy Code Coach, which is live support for any of your energy code questions. You can reach us by the means below. We also offer training and support similar to what we're doing today, and regional forums that we're moving to a biannual occurrence for networking and education. Next. The course that we're taking today is through our Building Performance Training Program, which serves current and prospective building professionals in technical and soft skills to help workers thrive in the evolving industry of building performance. Next. And our final program is our Home Energy Savings Program. This is for property owners of multifamily units that have 5 or more units. We offer rebates for heat pumps and additional energy saving measures. And then for single families to get you in touch with contractors and get paid for metered energy savings. Next. All right, so that is it from me. Again, feel free to message me in the chat privately or directly if you need anything, and ask any questions that you have, and I'll make sure that Russ sees them. So thank you all very much, and take it away, Russ.
Awesome. Thanks, Gray. Well, hi, everyone. Welcome. It's nice to be here. Hope everyone's having a nice day. It's a bit chilly out here. I'm up in Northern California, just south of Sacramento. And so welcome to this class. It's called Introduction to Residential Comfort Diagnostics, or Diagnosing Heating and Cooling Problems in Homes. My name is Russ King. My company is Coded Energy, and we developed Quick Model 3D. It's a new load calculation and duct design software. And my background is mostly residential HVAC design. I've been doing it for over 30 years, energy modeling and things like that. And I had the opportunity to manage a couple of mechanical engineering departments in my career, and they both specialized in the design of HVAC systems for residential production homes, meaning homes that are being built multiple times on the same subdivision. So we would get, a builder would send us 3 or 4 plans, model 1, model 2, model 3. We would do an HVAC design on it, and they would then bid on that. And the winner, whatever contractor won that bid, I would work with them to sort of fine tune the design to their preferences, and making sure all along that we had good airflow, good equipment sizing, and things like that. But one of the very interesting things, and probably one of my favorite parts of my job, was some of our clients, some of these production home builders would call me up and say, Russ, we've got this other subdivision that somebody else designed, and we're having a lot of problems out there. The homeowners just aren't happy. And so I developed a process of diagnosing these problems. The first thing I would say is, all right, make sure all the equipment is running good. Make sure the air conditioner is properly charged. Make sure that the fan watts and amps and volts and ohms and all that stuff is good, and do all that stuff and make sure the equipment is working fine. And then I'll come out there and look at it. And I'll do a spoiler alert right now and say 9 out of 10 times the problem was poor design. They just didn't design it well. They undersized the ducts, oversized the equipment, and things like that. But to get to that point, to diagnose that problem, I had a series of steps that I would go through. And so that's kind of what I'm here to share today. I have 5 or 6 different versions of this same class. I have a 3-hour version. I have a 30-minute version. So if you've seen some of these slides before, I apologize, but I think it's an important thing to understand for designers. One of the best things about the jobs that I had is I got feedback from the field. We would do a design, and we had people out in the field called HERS raters, and that was part of our service that we provided to the builders, was to do the Title 24 energy code calculations. We would do the mechanical design, and then we had field testing, diagnostic testing out in the field. And so I would get feedback on our designs, on our plans, our actual mechanical plans. At each register, I would show the CFM, and there'd be a little box where they could write in the measured CFM, and then they would send that back to me. And so I got a lot of really good feedback, and that helped so much. It really gives you confidence in your design and the ability to be able to stand behind your design. And if a problem did come back on one of our designs, I was very confident that it wasn't our design that was causing the problem, but I had to prove that. I had to go out and show them, what the real problem was. And so I developed a series of tests, a process to go through to help diagnose the problem, and then of course make recommendations to fix it. So that's what this class is all about. And sometimes my page down button works and sometimes it doesn't. Very odd. There we go. All right, so let's talk about the different types of quote unquote comfort problems. The main one is temperature issues, okay? Hot upstairs, cold downstairs, and stuff like that. Humidity issues. I just came back from a HVAC symposium in Florida, and man, are we lucky out here in California that this is a dry climate. Back in Florida and Louisiana and Mississippi and East Texas and South Carolina, all those places, they have very high humidity there. And humidity causes most of their problems. Humidity is almost never a problem out here in California, so we're lucky. Another problem, not really a comfort problem, but a comfort related problem, could be high energy bills, okay? Noise, you get a lot of complaints about noise, and then possibly dust too. You get a lot of places, a lot of HVAC related problems that'll actually cause your house to be a lot dustier than it might normally be, okay? So, but we're going to focus on the temperature issues because that's the primary complaint that we get out here in California, okay? So, a very common comfort complaint is uneven temperatures between floors in a 2-story house. So you got hot upstairs, cold downstairs. We call that stratification. A lot of people say, well, hot air rises, right? Hot air rises. Well, that's true in a way, but it's kind of a limited way to look at it. I like to kind of have this little pop quiz that I do. And let's say you have a supply air register, and I could make 120-degree air come out of that register and have that air fall to the floor like a cold fog. Okay, how would you do that? How would you make 120-degree air come out of the register and then just drop and settle to the floor like a cold fog? Okay, everybody says hot air rises, right? Well, I can tell you, I could do that. I could make 120-degree air fall like that. And the answer to that is kind of a trick question, but the answer is to make the room 180 degrees. So now you're blowing 120-degree air into a 180-degree room. It is the colder of the two air streams, and so it's going to fall. So it's not, don't think of it so much as hot air rises, think of it as hotter air rises. It's a relative difference, okay? So air that's warmer is less dense than air that's cooler, and the cooler air is going to want to get underneath the warmer air, and so the warmer air is going to go to the top, and the cold air is going to go to the bottom. Okay. Well, that really only happens when the system shuts off. Okay. When the system shuts off and the air has that opportunity to start stratifying, and the buoyant air will go up and the denser air will go down. But if the system is running, it's less likely to do that because it's mixing. It has velocity, it has velocity pressure, it has energy, and it's being blown into the room and it's circulating all around, it's mixing together. The best way to stop stratification is to remove that temperature difference between the two volumes of air, is to get it to mix as quickly as possible. So you take that, so normally you're blowing 120-degree air into a 70-degree room, is to get those two volumes of air to mix together as quickly as possible. Then you don't have stratification. The other thing is to get the system to run as long as possible. So what a common thing you're gonna see in a lot of this discussion is proper equipment sizing relative to the load calculations. Okay, it is very, very common, and it's just human nature to want to oversize equipment to quote unquote play it safe. Okay, so you oversize equipment, and what happens is then it short cycles. It runs for less time periods. It's running for shorter cycles for less minutes during the hour. Okay, and that reduces mixing. And when you reduce mixing, you increase stratification. So one of the big things that you need to do is you need to size the equipment appropriate to the load calculations, which means you got to do load calculations. Okay, and that's a big problem. A lot of people don't do load calculations. They just size equipment based on the square footage, and that's a recipe for disaster. Okay, so another temperature problem is uneven temperatures room to room. So even on the same floor, you've got some rooms that are hot and some rooms that are cold. All right. A real common place that happens is bedrooms over a garage. You'll see that they are typically well under conditioned compared to other rooms. And then for some reason, it's always the baby's room. The baby's room, you call a room a baby's room, you can almost guarantee that it's not going to be properly conditioned. That's just always, you go over to a house, oh, my house, I have having problems, and it seems like it's always the baby's room. So that's just kind of goes without saying. And another common complaint is like family rooms and living rooms that have big sliding glass doors on the back of the house, especially when those are facing west. And you got all that sun beating in the back room, and then, oh, my family room is like an oven in the afternoon. You hear that quite a bit. Okay, and we'll talk about those causes and solutions for those kinds of problems. Even within a room, if you have vaulted ceilings, even within a room, you can have cold air settling to the floor and warm air rising up to the top. So you can have an actual noticeable temperature difference between the floor and the ceiling within a room. Again, that's mixing. When you have a room with bunk beds in it, you get that complaint quite a bit. The poor kid sleeping on the top is roasting, the poor kid down on the bottom is freezing. Vaulted ceilings will exacerbate this problem. And then another common place is lofts, where you have a big, huge open room with a loft up in it, and that loft is going to be many degrees warmer than the floor down below. Okay, so again, this is a mixing issue. You want to really focus on mixing if you want to avoid these problems. Another temperature problem is the system just simply doesn't maintain temperature. They set it to a temperature and it runs and runs and runs and never cools off in the summer, or it never heats up in the winter. Okay, that a lot of times can be an equipment undersizing problem, which is actually quite rare. It's very rare to have a system that's too small for the house. Usually what happens is the equipment is properly sized, but there's something else preventing that capacity from reaching the house. It could be really leaky ducts. It could be the house is super leaky too. It could be undersized or undercharged refrigerant, things like that. But we've checked that already. So that's not going to be one of our potential problems. Another temperature issue is drafts. You're sitting in a room and you just feel cold air. You're not sure where it's coming from. You just feel cold air blowing across your body. Okay. Windows, when warm air comes in contact with a cold window, it becomes more dense and it wants to fall. It'll settle down, and that creates air movement. And sometimes that air movement can be felt. Okay. Around windows, around doors, again, vaulted ceilings. A lot of times in a vaulted ceiling, you'll have a wall up high, and if you were to drill a hole through that wall, you come out in the attic. We call that a knee wall. All right, so any wall where the back of that wall is an attic is considered a knee wall. And a lot of times those knee walls are very, very poorly insulated. There's just a fiberglass bat is just stuck up against it, maybe some spray adhesive, and they just stick the bat up there, and over time the bat just peels off. And then basically all you have between the house and the attic is just sheetrock and nothing else. You can get a lot of temperature variations being caused by that too. Okay. And then supply registers, air coming out of the register feels too cold. I have a register. I have a supply register right here under my desk. I'm standing up at the moment. But when I sit down, there's a register under my desk. And in the summertime, when cold air comes out of that register, it hits my knee, and my knee just gets really, really sore. It just aches because of that really cold air. And so our air conditioning system is oversized for our house, and the ducts are undersized, and it blows. I didn't design it, just throwing that out there. And it blows really, really cold air because of that combination of oversized equipment and undersized ducts. That makes the supply air temperature much, much colder, and it's blowing right on my knee, and it just makes my knee just really sore. So what did I do, being the mechanical engineer that I am? I took a shoebox, I took the lid off, I cut the end out of the shoebox, and I set that over the register to blow the air out the other direction. So there you go. Engineering school paid off. All right. So, but something that you're going to hear a lot about in terms of drafts as we start switching from gas furnaces to heat pumps is the supply air temperature coming out of a heat pump is not as warm as a gas furnace. And so homeowners are going to start complaining about drafts. They're going to say, oh, it's drafty. When the system turns on, it feels cold. Okay. It's not really cold. It's the air coming out of the register is warmer than the room air. So it's actually warming the room. It's bringing up the temperature of the room, but because that supply air is colder than your body temperature, it feels cold. When it blows across your body, it's cooler than your body temperature, so it's making BTUs leave your body, and that makes you feel cold. That's why ceiling fans work, okay? Ceiling fans moves the air, and moving air feels cooler as long as it's cooler than your body temperature, okay? So that's an issue. So supply registers, supply air temperatures, where the registers are located. ACA, Air Conditioning Contractors of America, you'll hear me mention this a few times. You've probably heard of Manual J, Manual S, Manual D. They also have a manual called Manual T that talks about where to put a register in a room, okay? And with heat pumps, you want to be very careful not to put a register somewhere that's blowing air directly on the occupants, because that air will feel cold. And so in an existing house where you've switched from a gas furnace to a heat pump, you don't have a whole lot of flexibility on where you put those registers, but you can certainly use different types of registers. Okay. All right. So one of the things that I've kind of developed is a process for interviewing homeowners. This was a very long trial and error process that I went through. And basically I learned over time to be very, very specific about what you ask a homeowner. I remember a particular problem house in Las Vegas where I was talking to the homeowners. I designed the house. I designed the HVAC system in the house, and the homeowners kept saying, "I'm hot. I'm hot. It's always hot in here." And what they meant was they're muggy. And it took me a long time to figure that out. I was like, the house is fine. The temperature's fine. And finally, the wife said, oh, when I'm putting on my makeup, it just slides off my face. I feel so sweaty. And I go, wait a second, you're muggy. And they go, yeah, we're muggy. And I said, okay, here's what I need you to do. I actually went down. I didn't have one on me, but I went down to I saw a cigar shop down the street. I went to the cigar shop, bought a little hygrometer. I calibrated it and I set it on their table. And I said, call me in a couple of days when you feel hot. And let me know what it says. And they called me back, and it was like 79% humidity inside this house. So I said, it's not a temperature problem. That's a humidity problem in Las Vegas of all places. And so what happened in that particular one was it was a retirement community, like a Del Webb community, little one-story homes. And they put shades on all the windows. They built an overhang on the back of the house. And what they ended up doing was actually reducing of the load of the house so much that the equipment turned out to then be oversized for the equipment. They were also in the best case orientation. And when the equipment's oversized, it short cycles. And what happens is when it short cycles, it also removes less humidity from the air. And so humidity was building up in the house. And they were so conscious about energy efficiency and keeping the heat out of the house, they never ran their exhaust fans. They didn't run it on their kitchen hood, and they didn't run it in their bathrooms. And so every time they took a shower, every time they boiled water on the stove, it made the house super, super muggy. Okay. So that was a big problem. That was actually a humidity problem in Las Vegas. It has like 0% humidity outside. So those are the kinds of things. But the point is that it was the last thing I expected of a house in Las Vegas, and I couldn't figure out what they were trying to say. And so you need to develop a set of questions that are very specific about the symptoms. Okay, so identify the symptoms of the problems and use very precise terms when you're trying to identify how they feel. Do you feel warm? Do you feel cold? Do you feel muggy? Do you feel sticky? Do you feel sweaty? Do you have a dry nose, dry throat? Those sorts of things. So develop a set of questions that are very precise and have like a checklist so you don't forget to ask them certain questions. Okay. Ask them what seems to fix the problem. When you're having this problem, is there something you do or something that happens that resolves that problem? Okay. They say, oh, it's miserably hot until the sun goes down. Okay, that makes sense. Oh, it's miserably hot until I close the drapes. Okay, it's cold until I put on a sweater. Okay, that makes perfect sense. I have to turn off the vents to make the problem go away. Find out the other thing to find out, and this is really important. A lot of people forget to ask this question: is what rooms in the house are the most comfortable? What are your favorite rooms to go to? They'll say, oh, the baby's room is miserably hot. And then you'll say, well, what's the most comfortable room in your house? Oh, our master bedroom. That's the most comfortable room. That becomes your baseline. Okay. The most comfortable rooms is the room that you're going to compare everything to and look at that. All right. So that's an important question to ask. Then ask them when the problem occurs. Okay. Does it happen in the heating season? Does it happen in the cooling season? You know, sometimes they'll say, oh, it's hot upstairs. And I thought they meant, oh, in the wintertime. No, they're hot upstairs in the summertime. Okay, that's interesting. All right, because you got a lot more airflow upstairs, but you have to be very specific about what you're asking so that you're not misinterpreting what they're telling you. And this was an interesting question here, and a lot of homeowners don't realize this. Ask them if the problem is better or worse when the system is running versus when the system is off. Okay, and then they might say, I don't really know. I've never paid attention to that. And that's an important question to ask, okay? And it makes a big difference whether they're uncomfortable when the system's on or when the system's off. Most of the time, it's when the system is off. They'll say, yeah, the system shuts off, and then the bedroom just gets hotter and hotter and hotter and hotter and hotter. And then the system will finally kick on, and then the bedroom feels better, but it never really gets good, okay? And then the system shuts off, and then it keeps getting hotter and hotter and hotter, okay? So those are important questions to ask. Ask them if it's worse on mild days or extreme days. Usually it's going to be an extreme day that they're having a problem, but there are some problems that are actually worse on mild days than they are on extreme days, and that's usually a sign of oversized equipment. Because if equipment is oversized for an extreme day, it's going to be really oversized for a mild day. All right. Then ask them what time of day the problem is: morning, evening, afternoon, nighttime. All right, that's a good indication of a problem. And then ask them how they operate their thermostat and how they operate their doors and windows. And then, like the house in Las Vegas, another question I've learned to ask after talking to those folks: how do they operate their exhaust fans? Do they run their exhaust fans when they're taking a shower? Do they run their kitchen hood when they're cooking on the stove? Okay, those can be very important indications. And then, of course, where in the house does the problem occur? Is it upstairs? Is it downstairs? Which bedrooms? Which side of the house? East, west, things like that. All right, so all those kinds of things. You guys will be getting copies of these slides, by the way, and you can use these slides to sort of develop a set of questions for you. There you go. All right. So, like I said, the first thing, before you start diagnosing comfort problems, you have to have a technician out there to make sure that the equipment is running better, okay? So you have to resolve any equipment issues first. A big one is refrigerant charge. Make sure the system is properly charged, okay? After all the equipment issues have been resolved, then you can start diagnosing other types of problems. So in other words, the equipment is performing as it should, but the homeowners are still not comfortable, okay? So once faulty equipment has been ruled out, there's really only 3 things that cause the vast majority of comfort problems. The first one is the homeowners are not using the system correctly, all right? This is a big issue. occupants are behaving detrimentally to the performance of the system. And the best or the most common example of that is they don't operate their thermostat correctly. Too many homeowners think that they can turn the system off, go to work, come home, and have a blazing hot house, turn the system on, and expect the house to cool off quickly. Okay, that is not how systems are designed to work, and that's not how they're supposed to work, and that is not an efficient way to run a system. So they should not be doing that. So that's an education issue. But you can also have homeowners who, like, say, oh, we leave our windows open on this side of the house because we like the fresh air coming through. Well, that adds a tremendous load to the house, and the system may not keep up. So look for occupant behavior issues. I had an interesting one at another house in Las Vegas, and I designed the heating and cooling system in this house. And these homeowners had a downstairs master bedroom, and they said that their master bedroom was always hot. And I said, okay, well, I'll come out and look at it. And so I came out and looked at it, and it was a huge, huge master suite. They had a little sitting area over here. They had some, palm trees and planted palm trees and stuff like that. It was really nice house. And I go, it is hot in here. That's very unusual. And I noticed one of the palm trees over in the corner behind a couch. The couch was kind of pulled out from the corner. This palm tree was moving. I went, oh, that's interesting. There's no register over there. And I walked over and looked behind the couch, and there was about a 3-foot by 2-foot doggy door that they had put in the wall, and the flapper on the doggy door was moving like this. So when the system turned on, it was pulling hot air, 110-degree air from outside. It was pulling all that into the bedroom through a big doggy door. I said, all right, there's your problem. This is not a design problem. You guys need to do something about this doggy door. So that turned out to be it. So anyway, that was just poor occupant behavior. You can't put a huge doggy door in your exterior wall of your house and expect that room to stay cool. The other one is the load of the house is higher than it should be. So the load calcs were done on the house, the equipment was sized, but then something about the house, the loads are much higher than they anticipated when they did the load calculations, okay? So a lot of times in new construction, when you do a load calc, they will give you a set of plans and they'll give you a set of energy features, and you use that information. And so you're assuming that the house is being built correctly. A lot of the ones that I ran into that were comfort issues related to this problem, back when low-E windows were very popular, or first started becoming popular in production homes, probably the late 90s. Low-E windows were kind of the new thing. The new code came out and required or kind of really encouraged people to put low-E windows in their homes. Well, there was this huge demand for low-E windows, and the low-E window manufacturers couldn't keep up. And so what would happen is they would have this huge truck of windows, and they're waiting for 3 or 4 more windows to be manufactured so they could put them in this truck and send them off to the subdivision. And I think somebody in the warehouse goes, you know what, let's just throw some clear windows in. They'll never know the difference. We'll just throw some clear windows in. And then the truck goes off, they install all these windows. And then guess what? The rooms that have the clear windows, when you did the load calcs for low-E windows, will not be comfortable, especially if they're facing west or southwest. And we actually had this happen quite a bit, especially in Las Vegas. We had this little tool. It looks like kind of like a stud finder, and you could put it on a window and press a button, and it would tell you whether it was a low-E window or not. And it would tell you which pane had the low-E coating on it. So it was a cool tool. And we'd go out to these houses, and they say, oh, the baby room's not comfortable. And we'd go out there and we take this little tool and push it on there and go, oh, it's a clear window. It's not the right window. And so that would be the problem. So there's things like that. Another problem we occasionally ran into was you have a 1-story house, and maybe there's 2 bedrooms on the front of the house, kind of poking out off the front of the house, and the roof. There's something called California framing, where the roof sheathing comes all the way down, and then they frame on top of that roof panel, and they frame out these 2 bedrooms off the front of the house. But in order to access that attic, you have to cut a hole into that roof sheathing and go through that hole to get to that other attic. And we call that California framing, is where that roof sheathing comes down and they build on top of it. And what happens is, in this one particular case, is these 2 bedrooms were not comfortable. And so I went out to this house and looking around, and I could feel that, yeah, these rooms are really uncomfortable. And the other thing I noticed is that when the system turned off, it got worse really quick. I mean, when the system turned off, it got hot fast. And I thought, that's interesting. And then I realized there was actually radiant heat coming off the ceiling. The ceiling was super hot. And I took a little laser thermometer, I poked it up there and I said, yep, there's something wrong. So we went up in the attic. They had never insulated over the top of those 2 bedrooms. They never went through that hole to access those 2 bedrooms out there, and they never insulated the ceiling. So these 2 bedrooms had a really hot attic with no ceiling insulation, and that heat just radiated down into the space. So that's another type of system, type of issue. Then number 3, the system is not designed well. They just didn't do a good job on the load calculations. They didn't do a good job on the equipment selection, and they didn't do a good job on the duct design. That's very common. The vast majority of comfort problems are caused by poorly designed systems, okay? So diagnosing comfort problems, one of the best tools you can use to diagnose comfort problems is the design process, is understanding the design process, okay? So the good news is that design problems are fairly easy to diagnose. If you understand the design process and you can sort of do a design on the house, a quick and dirty design, and say, okay, here's what I think it should be, and then you compare that to what they actually did, that is an amazing way to find comfort problems, okay? So I call that an after the fact design, or some people call it, you might call it an as-built, but it's a as it should have been built kind of design, okay? So you basically have the house, you have the information about the house, you do a quick load calc, you do a quick, say, this is what I think the equipment should be, you do a quick duct design, and you figure out what the airflows to each room need to be and what the total airflow needs to be, and you compare that to what's actually going on in the house, and you can find problems really, really quickly, okay? Especially on the sizing, That's probably the most common problem I run into that causes comfort problems is oversized equipment. And oversized equipment doesn't run as long, it short cycles, and that will cause comfort problems, okay? So you do a quick load calc, you say, okay, I think my load calc says this needs to be a 3-ton system. You look at the house, 4 tons, up, great, 33% oversized. Needs to be a 2.5 ton. Oh, they put in a 3.5 ton. You know, things like that happens all the time. It's just human nature to want to go up a size to play it safe, and it really should be the opposite. You should go down a size to play it safe if your concern is comfort issues, and oh, by the way, energy efficiency too. If your concern is comfort and energy efficiency, you should always round down a size whenever you have the opportunity to do that. Do not go up a size. That is a recipe for more comfort complaints, okay? So you compare equipment size, you will compare duct layout and register locations, and then you can compare duct sizing and airflows, okay? Those are the 3 big things that you get from doing a after the fact design and comparing it to the existing building. All right, so how do you evaluate an existing system for proper equipment sizing and duct sizing? Well, doing a proper design on a house is a good and important investment in time, okay? It's worth it. If they don't have, if the homeowner doesn't have that information, and a lot of times I could get that. A lot of times I could get the other person's design because I mostly dealt with new construction and homes that were only a year or 2 old. And I could just look at the other designers, you know, design and point out right away where the problem is, okay? So the ability to do a good design is really, really important. But it's also possible to do a really quick and dirty sort of evaluation without doing full on load calcs, without doing all this other stuff. There's a way to look at a duct layout and just kind of do a quick analysis to see if it's worthwhile, or if it's reasonable, if it's even in the ballpark, okay? And let me show you how to do that. By the way, this is a blog article. I have a blog. Here it is down here. It's called russellking.me. And I gave myself permission to use on my blog article, by the way. And I have several articles there. This particular, the next few slides comes directly from a blog article. So if you want to see more information about it, you can go check it out there. And what happens is I get a lot of people will just like the hardest one is when they verbally describe their duct design to me. Oh, I got this size duct going to here, and I got this size duct going to there. And then they say, does that sound right to you? I'm like, well, can you at least sketch it out for me? And then I get a lot of people just kind of sketch it out. I've literally had people draw duct designs on a cocktail napkin in a bar and say, does this look right to you? And I can do it. I can look at it. An interesting thing, kind of a funny thing, is my business card. Here's my business card. On the back of my business card, I have what's called the world's smallest ductulator. And it's actually a little table of duct sizes relative to airflow and friction rate, okay? And I used the ACA wheel, and I created this little table. And I can literally use my business card to evaluate a hand-sketched duct layout. And I'll show you how I do that, okay? So the first thing is that we have to assume good airflow. And good airflow very commonly is assumed to be around 400 CFM per ton of cooling. So we're talking about a system with air conditioning. And that's a reasonable number. In humid climates, they actually don't want that much. In humid climates, they want less airflow to improve the latent removal, so the moisture removal from the air. But in a dry climate, you want no less than 400. By the way, the Title 24 Energy Code requires at least 350. Think of 350 as a D minus, all right? If you're at 349, you fail. So 350 is not a good target. You want to be around 400. I would regularly design to 500. I know people that design to 600 CFM per ton, okay? And that, when you improve airflow, you improve system capacity and you improve system efficiency. So, and the converse is true too. When you reduce airflow, you reduce capacity and you reduce efficiency. In other words, let's say you have a 2.5 ton system and it should be moving around 400 CFM per ton, which is about 1,000 CFM, okay? And if you were to install a duct system that only gave you 700 CFM, that system, not only is it going to have less capacity, it's going to be less efficient. So let's say that 2.5 ton is probably going to be more like a 2.25 ton. And if it's a 16 SEER air conditioner, it's going to be more like a 15.5 SEER air conditioner, simply because the ducts are undersized, okay? So assuming that good airflow is around 400, that's kind of my bottom line. Anything less than that is not good to me, okay? Is 400 CFM per ton. So we're going to use that number to evaluate a duct system. So here's a very simple sketch, okay? It's a little horizontal unit up in an attic. It's a 3.5 ton system. It's got 4 10-inch trunks coming off the supply plenum, and they split into 2 8s and a 4 and an 8, 2 8s, 8, 6, 4, 4. You can see all the duct sizes there. It's got a 16-inch return on it. Okay, it's very typical, very common, what I see a lot in existing homes. Okay, and so somebody sketches this out and shows it to me and says, how does this look to you? Does this look okay to you? And at first glance, I'm like, yeah, it looks a little undersized, but how do I know that? How do I know that the ducts are undersized? So I start with the 400 CFM per ton. So 400 times 3.5, we get that number, and that's gonna be 1,400 CFM per ton. So that's our target. And we know that all of the air is going through these 3 main trunks, these 3 10-inch trunks, okay? We also know that all the air, by all the air, I mean the 1,400 CFM, so we know all the air is going through those 4 trunks right there. We also know that all of the air is going through all of the registers, the supply registers, okay? So all the air is going through all those supply registers. Now there's some intermediate trunks that we're not really sure about. This 8 here, this trunk, the 6 here. We're not going to worry too much about that. We're going to look at all the supply registers. We're going to look at the 4 main trunks. And then we also know that all the air is going through this one return duct here, okay? So by knowing that all the air is going through those, we can add up what we think should be going through those and compare it to what we want to be going through those, which is 1,400 CFM, okay? So this little table, this is very similar to what's on the back of my business card. I just took the ACA duct sizing wheel for flex duct, and this is based on a friction rate of 0.1, okay? And I take the 0.1 and I go to a 4-inch duct, and I say at a friction rate of 0.1, how much air should I get out of a 4-inch duct? And it's 20 CFM. And then I go to a 5-inch duct, and then I go to a 6-inch duct, and I just create a little table like that. And the back of my business card is very similar, but I did it for a bunch of different friction rates, okay? 0.1 friction rate is a really common friction rate. And if you were to do 1,000 designs that look kind of like this layout here, they're going to average out to have a friction rate of about 0.1, okay? But you shouldn't just use 0.1 to design a system. You should calculate the actual friction rate for that system and use that friction rate to size the ducts for that system. And friction rates can vary from system to system. I have another article on my blog. It's about friction rates. So if you want to learn more about friction rates, go to my blog and search for friction rate. Okay. But we're just going to use 0.1 because it's a very common number. And if you notice on a lot of ductulators, I have a whole collection of ductulators. It just happens to be just out of my reach. Let me grab it here. Here's that ACA duct wheel I was talking about. This is a great one because it's very accurate and it has multiple duct types on it. It has sheet metal, duct board, and flex. This is my ductulator collection here. Okay. Some of these are for flex and some of these are for sheet metal. And a lot of them, the 0.1 is sort of highlighted on there as though you're supposed to use 0.1, but you're not really supposed to use 0.1. That's just kind of it's kind of a common number to use. Okay. But you should always calculate the actual friction rate. All right. So anyways, that's where this table comes from. Let's see, for examples, that's the blog article. It's called Friction Rate Explained, maybe. Friction rate's a really kind of a weird number to comprehend, but after you've used it for a while, you kind of start to get used to it. All right. All right, so the first thing you do is you look at this duct layout and list all the main trunks, all the trunks coming off the supply plenum. Just create a little list and then use that duct wheel or that table to say how much air should I be getting through those trunks. So this system has 4 10-inch trunks. And if you go to the table, 10-inch trunk should give you about 300 CFM, okay? So you write that down, 300, 300, 300, you add that up, 1,200 CFM. Ooh, that's not good. Remember, at 400 CFM per ton, we want 1,400 CFM to be moving through that system, but this duct system will only allow about 1,200 to move through at a friction rate of 0.1, okay? Now you can cram a lot more air through there, but then what happens is you start reducing that 400 CFM per ton is no longer gonna be there. All right, so there's our trunks. We already know that our 4 10-inch trunks are a bit undersized for a 3.5 ton system. Let's look at the supply branches. You add up all the supply branches, 84, 888, 44, 88884. All right, you use this table, and 8 should give you 170, a 4 should give you 20. And that's all there is. You add those all up and you only get 1270. So now we know that all of our supply branches are undersized for 400 CFM per ton. So that's a problem. All right, now we look at the return. We got a 16-inch return on a 4-ton system or a 3.5 ton system, 16-inch turn, 1,050 CFM. So we're in deep trouble, okay, on our return. Our return is designed for 1,050 CFM. If we want 400 CFM per ton, that ain't going to cut it. All right. All right. So we compare all those to the desired target and see if it works. At 400 CFM per ton, which I think I'll call that a B grade, all right, we're not good. At the D- grade of 3.5 tons, we're not good even for that. So we would fail the minimum airflow requirement for Title 24 in California at 350 CFM per ton. We're at 1,050 on the return. We're at 1,200 on the supply trunks, and we're around a little bit more than that on the supply registers. Okay. So I don't think we would pass the 350 CFM per ton. So no, this is not a good design. This is a bad design. All right, we're at 1,200 here, 1,050 on the returns, 1,270 on here. We want 1,400 CFM. It ain't gonna work. All right, what should it be? You could go back and say, let's bump this up to a 12. Let's bump that up to a 12, and then you can start redesigning the system and know whether it works or not. Okay, so that little exercise I just did is a quick and dirty way to evaluate an existing duct system to see whether it's going to meet the airflow. Okay, and it's all based on using this very simple little table. All right, there we go. So as you can see, the ducts are well undersized for a target of 400 CFM per ton. This is especially true for the return, which is a very common problem. It's very, very common for returns to be undersized. The good news there is that by simply fixing the return, you can have a big impact on the airflow of the system. So improving return airflow is always a good thing to do. You can put in a bigger grill, you can put in a bigger return duct, but what I usually suggest is just add another return. If there's a 24 by 20 return in the hallway is I'll say, let's put another one of the exact same size right next to it. That way they use the same size filters. They've doubled their return capacity, and it will actually help the entire system work better. A simple fix is increasing the return capacity, and you might be able to get it up to the 350 CFM per ton. But are you satisfied with a D- system? I would not be satisfied with a D- system. So you might be able to get it up to 350. They might notice an improvement. They probably will notice an improvement. But whether that's good enough, it just depends. Okay. All right. So note that this does not address the room by room air balance. We don't know if that 8 is the right size for that room. We don't know if that 8 is the right size for that room. In order to figure that kind of stuff out, you got to actually do load calculations. So all I did was I just said, does this entire duct system have enough capacity to handle our target airflow for the whole thing? Now, I will tell you this too. If it does, if your duct system will have good overall airflow, that will forgive a lot of sins. And what I mean by that is if you have good overall airflow, it is much less likely that they're going to notice some balance problems between two rooms. So let's say this 8 and this 8, these two rooms, that maybe these two rooms don't have the exact same load. Maybe this should have been a 7 and that should have been an 8. Okay. If the airflow starts getting pinched off and starts getting reduced, you start noticing those kinds of differences sooner. But if you have good overall airflow, you've got good mixing, and you have good equipment sizing. The equipment's going to run for longer cycles. That airflow is going to mix, and you're not going to notice that maybe that room should have had a 7 instead of an 8. Maybe that room should have had a 9 instead of an 8. You're not going to notice that as much if you have good overall airflow. Okay, but let's say you do have good overall airflow, and there's still the rooms aren't comfortable between each other. Then that means there's a pretty serious air balance problem going on. Okay. In order to determine actual target airflows on a room by room basis, you got to do room by room load calculations. Okay. So ACA, Air Conditioning Contractors of America, they have their 3 main design manuals, Manual J, Manual S, and Manual D. J is load calculations, room by room load calculations. S is equipment selection, picking a piece of equipment that'll match those loads. And then Manual D is duct design. Okay. You need to do that process if you want to do proper air balancing. You can't just guess. You can't just go in and say, oh, I think this room has got too much air. I think this room is not enough air, and then just start messing around with it. You need to know, because it's all about relative airflows compared to the other rooms. Okay, that's an important concept. All right, so here's the ACA manuals, the 3 main ones, Manual J, Manual S, Manual D. They have a bunch of other manuals. I mentioned Manual T, it's for terminal selection, that's picking registers. They have a residential design overview. They have one for heat pumps. They have a new one out for low load homes, okay? And then they have a whole bunch of standards and checklists that you can actually download for free. Quality installation checklist, the quality maintenance checklist, things like that. They have a standard for cleaning coils. They have a standard for that. So I encourage you to go to aca.org and look for that stuff. All right, so load calculations. Load calculations are critical to properly sized heat pumps. All right. Also, to a certain extent, heaters as well. Undersizing equipment will cause a house to not cool well on very hot days. So if the equipment is undersized, the equipment has a capacity less than the load calculation of the house, when it gets really hot outside, that air conditioner doesn't have the capacity to cool that house off. So what happens? The air conditioner runs and runs and runs and runs and runs, and the house starts getting warmer and warmer and warmer. Okay, that's what happens when you way undersize a system. But that's only on very hot days. On mild days, it works great. Okay, on mild days, it works great. Same thing on the heating side. An undersized heater, when it gets really, really cold, it can't keep up and the temperature starts dropping a few degrees below. Okay, that's what happens when you undersize, but you have to really, really undersize equipment for that to be the case. Okay, oversizing equipment causes a lot more problems that will cause comfort issues. Oversizing equipment, the equipment runs for shorter periods of time. You get less mixing, you get more stratification. Remember, one of the most common complaints is stratification in a house. You get uneven temperature distribution. You have higher electric bills, and short cycling will reduce equipment life. And if you live in a humid climate, short cycling increases humidity because it doesn't run as long to remove that moisture. All right. So I will tell you 100% that oversizing equipment causes more comfort complaints than undersizing equipment. But it's always human nature, and I'm guilty of it too. When I'm looking at it, I'm trying to pick a piece of equipment for this house. I'm like, oh, should I go to a 2.5 ton? Should I go to a 3 ton? What should I do? What should I do? The tendency is to want to go bigger so that you don't have comfort complaints. But guess what? Going smaller is less likely to have comfort complaints than going bigger. Oversizing equipment causes more problems than undersizing equipment, comfort problems, okay? All right. The negative impacts of oversized equipment can be reduced with multi-stage or variable capacity equipment, okay? So if you oversize the equipment on the milder days, when it's really oversized, variable speed and multi-stage equipment can throttle down and match the load better, okay? But don't let that be a Band-Aid for not doing a good design, okay? I've seen too many people say, okay, here's my load calc. I'm going to upsize it, but I'm going to use a variable speed equipment so that it can come down if it needs to be. Well, you've just sold them way more equipment than they really need. All right. It may never run on those higher speeds. Okay. Properly size the equipment, and then variable speed and multi-stage equipment works great on the mild days when it doesn't need as much capacity. That's the whole purpose of variable speed equipment, is that it can throttle down when the load is less. Okay, that's the reason they make that equipment, is to throttle down when the load is less, not to have excess capacity for those really high days. That's not what it's for. That's not how you design it. It's not what Manual S says to do. All right. Oversight, the negative impacts of both oversized and undersized equipment. Either one, the way to reduce the impact of that is to have good airflow and good duct design. Good airflow and good duct design will forgive a lot of sins, including air balance issues, including oversizing issues and stuff like that. Okay, so that's very, very important. Historically, the most common method of equipment sizing in California and a lot of the rest of the country was rule of thumb. How many people have heard of 500 square feet per ton or 450 square feet per ton or 600, whatever it is? It's a very, very common thing to do. And I will, in the back of the mind, it's always there. When I do a load calc and I pick a piece of equipment, I will always calculate the square foot per ton. And that's always in the back of my mind. That's not a good way to design equipment. That's not a good way to select equipment. First of all, floor area has very little impact on loads. Windows has way more impact on loads. If someone said, oh, I do X hundred square feet of windows per ton, I would have much more respect for that than if they did square feet of floor area per ton. Okay. It's just a bad thing to do. I teach a full manual JS&D class, and I have an example house where I can turn that house 90 degrees, and the load goes from 3.5 tons to 5 tons. The equipment sizing goes from 3.5 tons to 5 tons just by turning the house 90 degrees. I didn't change the floor area. All I did was turn the house 90 degrees. So that should show you right away that using 500 square feet per ton is obviously missing something very important, and that is windows and window orientation. Okay. So rule of thumb, and then the other was trial and error. So it was very common for people to do a house, oversize the equipment, and then the homeowners complain. You're like, oh shoot, homeowners are complaining. All right, next house I design, I'm going to bump it up half a ton. And so equipment has evolved to be bigger and bigger because they had an oversizing problem, but they thought it was an undersizing problem, but it was really an oversized problem. So on the next house, they made it bigger. On the next house, they made it bigger. And then the other problem is that ducts, architects do not give us room to run ducts. And that's a huge problem. And so, they'll say, oh, I really wish I can get an 8-inch out to this room, but only a 6 will fit. And so they run a 6. And they find, oh, it's cheaper and it's easier to run ducts if they're smaller. And so ducts have evolved to get smaller and smaller, and equipment has evolved to get bigger and bigger. And that's the opposite direction they should be going. Equipment should be getting smaller and ducts should be getting bigger, would be a better way for things to go. All right. So a really, really common cause of comfort complaints. In fact, I would say 95% of the problems of the houses that I tested, the problems were oversized equipment undersized ducts together, both of those things, okay? So the importance of good design, duct sizing. Since the temperature of the entire house is determined by one location, assuming a single system house, which is the thermostat location, it is very important in order to get even distribution throughout the house is to have the ducts properly sized to send air to the rooms at a rate that they need in order to maintain a constant air temperature in the house. Well, how do we know that? How do we know how much air that room needs? How do we know how much air that room needs? How do we know how much air that room over there needs? Well, you got to do room by room load calculations, okay? And then you got to take each room's load and figure out what percent of the total is each room's load. So you take the room load, divide it by the total load, you say, okay, that room is 10% of the load. What does that mean in terms of airflow? That room needs 10% of the air. So the airflow to each room is proportional to that room's load. So you need to figure out that percent for each room. If that room is 10% of the load, it needs 10% of the air. If that room is 7% of the load, it needs 7% of the air. So you take that 400 CFM per ton and divide it up into those percentages, and you distribute the air like that. That way, when the system comes on, it's sending air to each room proportional to the need of that room, to the load of that room. And that's how you get an even temperature throughout the house. Now, it's not a perfect way to do it because everybody knows that as the sun passes through the sky, the load on the rooms change. So how do we overcome that? Good overall airflow. So you got good mixing and proper equipment size to make sure the equipment's running for longer periods of time. So even in the morning when the sun's on the east, you get good balance, as when the sun is on the west, you get good balance, okay? Your airflows to each room is not going to be perfect, but good overall airflow, good mixing, and long run times help solve those problems, okay? All right. Target room airflows need to be determined by room loads. You need to know the relative need of each room. I call that the fair share of air, all right? Fair share of air. That means if the room is 10% of the load, it needs 10% of the air. It's that room's fair share of the air. Overall, undersizing of ducts, especially return ducts, and I mentioned this already, will reduce total system fan flow, which reduces capacity and efficiency. It's a double whammy. When you undersize ducts, it hurts you two ways. It reduces that system's ability to heat and cool, and it reduces that efficiency, whether it's the SEER or the AFUE or the HSPF. It reduces those numbers. You can see that right in the OEM tables, okay? Undersizing one or two ducts relative to the rest of the house can cause poor air balance. This will result in uneven temperatures in the house between rooms. So you got some rooms warmer than others. And this gets worse and worse and worse as you choke off the airflow. If you undersize return ducts, as you undersize all the ducts and the airflow per ton, that 400 CFM per ton drops to 350 or 325 or something like that, okay? That's when these problems really start to show up, all right? So it looks like we got a question in the chat here.
Yeah, Russ, I just got one participant messaged with a concern that you're mostly talking about cooling sizes, and they're from Santa Maria, where most homes don't have AC. So I just wanted to see if you could address that for a moment.
Yes, everything I say about cooling pretty much still applies to heating. It's just that the difference is that in heating mode, BTUs are leaving the house and you're replacing them by blowing warm air. And in cooling mode, BTUs are coming into the house and you're removing those from the house, okay? So everything I'm saying applies to both, okay? It's just that most homes in California have both heating and cooling tends to be the more common comfort complaint, all right? But everything I'm saying is perfectly true in both heating and cooling. Longer run times are better. Oversizing is a problem on extreme days, and oversizing is a problem on mild days, which is most of the time. Undersizing is only a problem on extreme days, which is a very small percent of the time. Everything I say is true for both. Yeah, thank you for pointing that out. Okay. And the other thing was on a furnace, not so much, on a gas furnace, not so much, but on a heat pump, low airflow will reduce capacity and efficiency, okay? On a furnace, low airflow, what it does is it drives up your supply air temperatures, which makes the air blowing into the room hotter relative to the room, which increases stratification. Okay, same issues, it's just opposite direction of heat flow, right? Okay, alrighty. So remember, equipment cannot be properly sized unless you know the load of the house. You can't guess. You can't just say, oh, 500 square feet per ton, or, oh, this house used to have a 4-ton, so I'm going to put in a 4-ton, or, you know, and tons can be heating or cooling, heat pumps. You have to do a load count. You know, you've heard the expression, measure twice, cut once. Okay, measure twice, cut once. I'm actually more of the measure once, cut twice school of thought. That's kind of my MO is, you know, I measure once, I cut it up, doesn't fit, I go back, cut it again. What about people who don't measure at all? If you're guessing on the load count, you're not measuring at all. You're not measuring twice, you're not even measuring once, you're not measuring at all. You have no idea what it's going to be. So you got to do a load count, and that's manual J. Okay, and think of the load as what the house needs. That's the demand. The house needs a certain amount of heating and cooling. The load count is the demand. Manual S is equipment selection, but think of S as supply. S is what you're providing the house. The house needs something and you're providing it with equipment. That demand and that need have to balance. Okay, equipment cannot be properly sized unless you determine the capacity at design conditions. That's important. Furnaces, not a big deal. Heat pumps and air conditioners, the amount of heating and cooling that a compressor driven equipment will provide you is very, very dependent upon where and how it's located. What are the conditions in which it's operating? What is the outdoor temperature? What is the indoor temperature? What is the humidity? Okay, all of those things affect capacity, and you have to figure that out. You can't just guess. You can't just say, oh, it's a 3-ton system, a ton is 1,200 BTUs, so it's going to give me 36,000 BTUs of heating or cooling. Okay, you have to look at design conditions and see what it's really going to give you. As it gets colder outside, heat pumps don't put out as much heat. As it gets hotter outside, air conditioners don't provide as much cooling. Where you get that stuff? Read Manual S. It'll tell you how to determine actual design capacities at design conditions by looking at the OEM, they're called the expanded data tables, or the OEM capacity tables, things like that. There's tables that'll show for different outdoor temperatures, for different indoor temperatures, for different airflows, and you find a little table and you find what you look at. Sometimes you have to interpolate between columns, and it'll give you the exact capacity for design conditions. That's what you should be using. Don't guess, okay? Remember, individual ducts cannot be properly sized unless you know how to distribute the air. And to do that, you need room by room load counts, okay? You've got to do that. To obtain the load counts, you'll need to take a Manual J class. I offer lots of Manual J classes. PG&E has them, SoCal Edison has them. They use our software, they use other softwares. My buddy Gary Wolin teaches a good class for PG&E. He uses RightSoft. The classes I teach use our software, Quick Model. Whichever software program you use, take a class on it, because you have to learn that software. You can know Manual J, S, and D inside and out, but once you use that software, the software is going to apply those things in a different way. So here's the 3 ACA approved software programs that do both load calcs and duct design. RightSoft has been around for years. I've used RightSoft since it first came out in the early 90s, and I used it for most of my career. Elite came out in the late 90s. It's basically a RightSoft clone. If you can use RightSoft, you can use Elite. And then in 2018, I convinced my son, who got a computer science degree from UC Santa Cruz, to help me design a load calculation program that I wish I had when I was doing all my design work back in the day. Okay, it's 3D, but whichever one you choose, take a class on it and learn how to use it. I also encourage you to join groups that use that software. There's a lot of Facebook groups out there. We have a Quick Model Facebook group. There's a RightSoft Facebook group. There's forums. Compare your results to other people's results. Have other people check your work. On our Quick Model Facebook users group, a lot of guys come in and say, hey, everybody, look at my design. How did I do? And people go, oh, that looks good, but you may want to do this, maybe do that. And it's a great place to get feedback. You can't do designs in a vacuum. You can't sit in a cubicle and do designs and throw them over the wall for somewhere else to use. You need other people's input. And if at all possible, have somebody test your designs. When you do a design and it gets installed, have somebody test it. If you can test it yourself, that's awesome. Please do. Or have somebody else test you and send back that information. What's my static pressure? What's my airflow at each register? Is it working? Are the homeowners happy? Is it maintaining temperature? Get that feedback. It's really, really important. Okay. So when you go out to a house, one of the things you're going to want to do is measure actual airflows. Okay. Supply and return airflows must be measured. So you did your after the fact design and you know what the airflows should be. Now you need to measure the actual airflows of the house to see how those match up and see where the problems might be. Okay. So how do you measure airflow coming out of a register? Well, one of the most common tools is a passive flow hood. Alnor, Shortridge, I'm drawing a blank, Alnor, AccuBalance, big scoops. So they have got these big scoops on it. You put it up, you push the button, and it tells you airflow. Okay. Be careful. Be careful with passive flow hoods. They do not do a good job measuring residential supply registers. Passive flow hoods do not do a good job measuring residential supply registers. They do a great job measuring returns because the air is being sucked up through the bottom. The problem with residential supply registers is they're usually directional. They've got their 3-way or 2-way or 4-way registers. The air comes out, hits the side of the passive flow hood capture box, and that air runs down the side. If you look at the bottom, there's a grid. And if all the air is hitting just part of that grid, it's not as accurate. You want the air to hit that grid evenly. So when on a return, it's pulling through the grid and it's measuring evenly. 24 by 24 hoods is very common. Those are designed for commercial registers. Commercial registers, the air is all coming out very evenly. Okay. And they work fine for that. They don't work well for residential supply registers. There's a way to trick it. Okay, there's a way to mess around with it. I don't have time to go into that, but that's what I use, a passive flow hood, and I got it to work. A better option, though, is a powered flow hood. A powered flow hood has a fan inside of it. You put it up over the register, and you adjust that fan to match the airflow coming out by getting a 0 pressure differential in the box, and then it measures the airflow that way. Very, very accurate. There's a company in Denmark that they sell them here. True Tech Tools, a bunch of other places sell them. Powered flow hoods, they work very well. You can do it with a velometer, but not super accurate. You can actually use a plastic bag and a stopwatch and do a reasonably accurate job measuring airflows. You see this LBNL 47382. Google that number, LBNL 47382. It's a Lawrence Berkeley National Lab study on how to measure residential supply registers. And they tested the plastic bag and stopwatch method, and it was one of the more accurate methods, believe it or not. Okay. The problem is it just doesn't look real good when you go out to a house, you put a plastic bag over the homeowner's register. It's like, what the heck are you doing? Okay. But it honestly, it really is. It's accurate. Okay. But anyways, they evaluate all these things and they'll talk about what I just said about passive flow hoods. They read about 15% high, the passive flow hoods. And that's all, I get all that information from personal experience, but it's all backed up by this Lawrence Berkeley National Lab study that they did. Okay. Now, when you're measuring air balance, you don't have to be super accurate in total. If you measure the return and you get a good measurement through there, that's your total system fan flow. That's a reasonable number to use. As far as measuring supplies, what you want is them to be accurate relative to each other, because you're looking at percentages. So if your flow hood is off by a little bit, as long as it's off by a little bit on all your measurements, it's not that big of a deal. Okay. Identifying balance problems. Should we compare actual measured flows to our target flows? So if we go out there and we measure 150 and our target says 175, is that automatically a problem? Is that automatically a problem? And the answer is no. Instead of comparing 150 to 175, what we should be doing is comparing the percent to the percent. Okay, and the percent is the measured airflow divided by the total airflow. So the only time you can ever compare your two measurements together is if your totals are the same. And chances are your totals are not going to be the same. You're going to have a target of 400 CFM per ton, but the measure might be 350. But when you're looking at balance, you have to compare the percentages to each other, okay? So here's an example. So this is a old spreadsheet I used to use a lot. And what I would do is, here's all the rooms, okay? I would add up all the airflow and I'd get 988. This is the measured CFM. The target CFM, the total was 1200. So I can see right there that the total is very low. So I can't compare this 195 to this 186 because what I should be comparing is the percentages. And in reality, this 195 is almost 20% of the total, and the 186 is only 15% of the total. This is actually quite a bit too high. Even though those two numbers are fairly close, the 195 and the 186, this number is way too high. It's 27% high, okay? Because I'm comparing the totals. So all this percent of total is it's this number divided by the total, and this number divided by the total, okay? So that game room was getting way too much air, and they noticed that, all right? So anyways, this was a kind of a weird example. I actually did the design on this house, and they didn't follow my designs. I had put a big register blowing 257 near the stairs because the stairs had a bunch of windows in it, and they decided they didn't need that register. And now the homeowners weren't happy, okay? And there should have been 257 CFM coming out of that register near the stairs. And instead, it got all crammed into the game room. All right, anyways, so that's what I'm looking at. So compare the percent of totals, compare these two numbers to each other, okay? You'll get copies of these slides, and you can, like, it's a really simple spreadsheet. You can put one together yourself. And then you say, what percent, how does this number compare to that number? Well, that's clearly a bad number. This is off by 27%. Okay. The other thing is, in your house, compare the total upstairs to the total downstairs, and you'll often find that the total upstairs is much higher than it should be. Okay. There you go. Now, what other tests are there that you can use to diagnose comfort problems? Well, if you think about a load calculation, okay, if you think about a load calculation, there's a lot of numbers that go into that load calculation. And remember I said that sometimes the house is not built quite like you thought it was going to be built. You know, they didn't put in a clear window, or they put in a clear window when it should have been low E. They didn't insulate over the bedrooms. Maybe the house is much leakier than you thought it was supposed to be. All those numbers that go into your load calculation, a lot of those, oh,
you gotta know what the water is.
Somebody's volume, there we go. Sorry, I lost my train of thought. A house is much leakier. A load calculation, a lot of those numbers that go into the load calculation can be tested. And infiltration is a big one, especially in existing homes. Infiltration can be a very large portion of a home's load, all right? And so if a homeowner is having problems, they're saying, oh, my system's not keeping up, you do a load calculation, you go, I think your system might actually be a little oversized, but it's acting like it's undersized, okay? Then it could potentially be the house is much leakier than you thought in your load calculations. Well, how do you check that? Test the leakage. You can measure the leakage in a house. You can hook up a thing called a blower door, and you can test the leakage. It's a big door with a curtain and a big fan, and it pressurizes the house and it measures the leakage. And you can plug that number, or you can compare that number to what you use in your load calculation. There's the problem. The house is way leakier than I thought it should be. Should you then suggest they upsize the equipment? No, you should suggest they seal the house, right? Okay, so that's the kind of test you can do. Let's see. Measuring static pressure in equipment is a really simple and really useful tool to help determine if the ducts are properly sized, okay? So a static pressure test is pretty straightforward. You just take a pressure probe, you take a reading there, and you take a reading there, you compare those two numbers. The return side is gonna be a negative number, and the supply side is gonna be a positive number, and remove the negative sign and add those two numbers together. And the difference between those two is your total external static pressure. If you can get the manufacturer's airflow tables, you can take that pressure to the airflow tables and see how much air that furnace is moving. and see whether it's close to the 400 CFM per ton target or not. Okay. The other thing is by comparing how negative the negative number is to how positive the positive number is, you can get an idea of whether the return is undersized. And that's a lot of times that's what you'll find is you'll take a reading on the negative side and you'll get a really negative number, and you take a reading on the positive side and you'll get a pretty low positive number. Okay. Well, that tells you right away that your return ducts are undersized. It's really, really struggling on the return side. Okay. So those kinds of things can be very useful. Duct leakage. Duct leakage can have a big impact. The symptom of poor duct leakage is the house gets pressurized or depressurized when the system turns on, but actually measuring the duct leakage is a very good thing to do. And while you're measuring, you may as well be sealing up there too. HVAC contractors, okay? Not HERS raters. HERS raters aren't supposed to seal when they're doing the duct testing, if they're testing for Title 24 purposes, okay? But while you've got this, while you're pressurizing the ducts, take a theatrical fog machine, pump smoke into the ducts, and you can see the leaks. Start sealing those up, okay? Infiltration, I mentioned the blower door test. Can have a huge impact on loads, okay? Infrared cameras. Infrared cameras don't actually measure anything except temperature of the surface, but what they do is they show you temperature differences. And that alone can be super, super informative. You can take an infrared camera and go around your house and you can see where they didn't install bats in a wall cavity. You can see where fiberglass bats or blown-in insulation is missing from a ceiling. You can see duct leakage, okay? A friend of mine bought one, and of course, the first thing he does is he takes it out of the box, he starts walking around his house. Okay, he's walking around this house. He's lived in this house for 10 years. He goes into the family room. It's a very long, narrow family room. And he's looking around, he looks up at the ceiling, and there's a big blue circle in the middle of his ceiling of his family room. He's like, uh-oh, I think I have a leak. I might have a plumbing leak up in the ceiling, because that you can see that. Any wet surface is usually cooler and you can see it. So it shows up in blue. So he goes up in the attic, fully expecting to find a leaky pipe. What does he find? A supply register in the middle of his ceiling that had been sheetrocked over. And he'd lived in this house for 10 years. And they had sheetrocked over a supply register in his family room. And he never would have noticed that had he not had that infrared camera. So he got up there, he cut it out, brought the boot through, put a supply register over it. Now his family room is way more comfortable than it was before. Okay, so those kinds of things can be found with an infrared camera. Data loggers. I have an entire class on data loggers. I have a video on my YouTube channel. If you go to Quick Model YouTube channel, I got a video about data loggers. To me, these are the ultimate tool for diagnosing diagnosing comfort problems. You put a bunch of data loggers around a house and you get some amazing information back from that. And data loggers have improved dramatically over the years. Back in the day, you see these data loggers here, these little things are about the size of a book of matches. You had to plug them into your computer, you had to start them, and then they would start measuring. You unplug them, then you put them in the house, you let them sit for a while, you bring them back, you plug them back into your computer, and you download the data. Well, the new ones are Bluetooth. The new ones you put in, some of the new ones even have a Wi-Fi base to them, and they'll send their data to the Wi-Fi, which will load it up to the cloud. And you can download without even visiting the house. Okay, so, but these are the old ones that I used to use. What you do with these is, well, what you can get from it, it'll tell you if the equipment's oversized or undersized. It'll tell you about air balance. It can also tell you if the homeowners are operating the thermostat correctly, okay? So the limitations to data loggers is you have to have pretty extreme temperatures for them to work well in order to get good data. All right, if you put data loggers in a house and it's a really mild day, the system may never run, okay? What you want to do is simulate the conditions where the homeowners are complaining. So you want to have a really hot day or a really cold day to do data loggers. Once you do that, once you have that, you can get some really, really amazing information back from these data loggers, okay? So here's what you do. Here's the trick. Here's my secret trade protected, patented, no, it's not. This is what I do with data loggers, and it's very interesting. You put one outside, put it on the north side of the house in the shade. You don't want the sun to shine directly on it, okay? That's going to measure outdoor temperatures. You put a data logger right next to the thermostat, off to the side. Don't put it above the thermostat because some old thermostats actually give off heat. So you put it off to the side, okay? Tape it right to the face of the supply register. Take a data logger or even take the register off, put it inside, put the register back on, okay? You want one to measure supply air temperatures. And then ask the homeowners what's their most comfortable house. Find a couple rooms that they think are comfortable, put data loggers in those rooms. And then the rest of the data loggers, put them in whatever rooms they're complaining about. Okay, so you got outside next to the thermostat on the register. You got a couple in good rooms, and then you have the rest in bad rooms. Okay, then you're going to let that sit for about a week or so. And then you're going to collect that data and you're going to plot it on a graph. And that graph is going to tell you some really, really interesting things. Okay. Tell the homeowners not to mess with the thermostat. Okay. I actually did some data loggers. I was an expert witness in a class action lawsuit against the builder. And I was on the builder side. I was helping the builder show these homeowners that their coat was actually oversized. They thought it was undersized. And so when I walked into these homes, I was the bad guy because I was representing the builder and they were suing the builder. So I had to have them sign a waiver saying, I promise not to mess with the thermostat. I will set the thermostat and I will leave it for the week of this test. I promise not to mess with the thermostat. I can actually tell by the data whether or not they're messing with the thermostat. Some of those homeowners did intentionally mess with the thermostat and say they didn't. So that's why I tend to call data loggers lie detectors, because they will tell you that. Okay. So try to monitor the house for about a week. When done, collect the data, graph it. Good software that comes with the data loggers will allow you to turn certain data sets on and off and things like that. Okay, but here's what you get. Okay, so here is a graph. It's 24 hours, and this red line is the outdoor temperature. So this house was in Fresno. The outdoor design temperature in Fresno is 98 degrees. And you can see during the test, it hit up to 106 degrees. So it got well above the design temperature for these houses. So you would think that if the equipment is undersized and the temperature is actually above the design temperature, that system is going to run and run and run and run and run and never cool off, right? That's what they thought was happening. Okay, I put these data loggers in there. That's not what was happening. But let's look at a couple rooms first. So this green line here is the thermostat setting. It's 76 degrees. And there's a green data line that tracks that very well. The temperature at the thermostat will go up and down a couple degrees. That's the dead band in the thermostat. Okay, but it's set at 76, so it should always stay right at 76. If the equipment is oversized, or sorry, if the equipment is undersized, it won't maintain temperature and it'll start to drift away. Okay, in heating mode, it'll drift up, and in cooling mode, or sorry, other way around. In cooling mode, it'll drift up. The house will get hotter, and in heating mode, the house will get colder if the equipment is undersized. Okay, but you can see it's the green line is staying right on the thermostat setting. But look at these two rooms here. These are actually these are east-facing bedrooms. And you can see that the temperature on a hot day, the temperature drifts up in the morning and then starts drifting back. Well, it drifts up in the morning and then in the afternoon starts drifting back down. Guess what? These were the two rooms they said were comfortable. These are the two rooms that they liked. Now, this is probably happening during the day when they're not home, so they don't realize it's doing this. But these are the two rooms that they said were comfortable rooms. So if it's drifting away and you can measure that difference and they think those are good rooms, what that tells me is a room has to be really, really bad before a homeowner will notice it. Okay. So let's see, these are the daylight hours. So you can see the outdoor temperature drops, then the sun comes up and it, the temperature shoots up. It peaks out about 3 p.m. and then the sun goes down and the temperature starts dropping off. And it just does that over and over and over every day. Okay. Very, very typical. Here's another house, different house. And you can see the green line is tracking the green straight line fairly well. It's drifting up, but barely a degree. That's not noticeable. But look at this room here. This is an under-conditioned room that when the thermostat was set at 78, it was getting up to 83 degrees. That is noticeable. And that was a west-facing room, okay? And you can see that it peaks out in the afternoon. And look at the other problem is that that room never gets down to the actual thermostat set point. It never recovers. it's always above. And in the afternoon, it's way above. At night, it's just a couple degrees above the set point temperature. But during the afternoon, it's way above, and it's noticeable. They complained about this room, and they have a valid complaint. Okay. As it turns out, this was not. They thought this was caused by undersized equipment, but I can still prove that it's not undersized equipment. Remember, I said you put a thermostat. So you put a temperature data logger right on the face of a supply register. That's this pink line. This line, whenever the air conditioner turned on, the data logger at the supply register, the temperature would drop. So it's measuring the supply air temperature. So it's going from room temperature to drops down to supply temperature. And then when the system shuts off, it starts to rise back up. So I can tell you by looking at this graph exactly when the equipment turned on and exactly when the equipment turned off. It turns on right at the beginning of this downward line, and it turns off at the peak at the bottom and starts drifting back up. I call these icicles, okay? This is a classic example of an undersized equipment short cycling, all right? So look at this. The design temperature is 98 degrees. It hit well over 100 degrees. If the system was undersized, right here at 98 degrees, this pink line should go down and stay down and run and run and run and run and run and run until it cooled off outside. It does not do that. It is well above the design temperature. And look at this, short cycle, short cycle, short cycle, short cycle. This equipment was oversized. And I proved that by doing load calculations and showing them and showing that it should have been, that it was oversized. They didn't believe me. I had to do data loggers to prove it to them. And this is proof. This is wonderful proof. But they did have a valid complaint. They just had the wrong problem. The valid complaint was rooms like this. Look at this room, drifted up to 88 degrees when the set temperature is 78. Okay. Look at this other blue room. It never recovers. You want to see something else weird about this graph? Look right here. When the outdoor temperature is below the thermostat set point, the set point 78, the outdoor temperature actually dropped below the thermostat set point. So it's actually cooler outside than the set point temperature. But look at these cycles. The air conditioner is running when it's cold outside. That should not happen. There's no good reason for that. That took us a while to figure that out. It turns out that this house had inadequate attic ventilation. So the attics were getting really, really hot, and that heat was staying inside the house. And even when it cooled down outside, that heat in the attic was causing the air conditioner to run in the middle of the night. This amazing stuff you can learn from these data loggers, okay? So, conclusions from this training. There's an entire arsenal of diagnostic tests that can be used to identify comfort problems. The most important tool is understanding the design process. Carefully and precisely identifying the symptoms that are causing the homeowner complaints is critical. Once the symptoms have been identified, the source can be confirmed and proven using diagnostic tests. Tests take time, but having real tangible measurements to show the homeowner, having graphs to show the homeowner, have data to show the homeowner is very convincing, okay? And the knowledge and skills to do these tests will set you apart from the competition. You know, your competition is going out there and going, oh, waving their hand, going, oh, I think your airflow is too high. Let's close off some registers. You come out there with a blower door and a flow hood and some data loggers, they're going to be very impressed, and you're going to be able to tell them exactly what's wrong with the house. All right, that's it. Thank you so much for your time. It is precisely, oh, it's 10:29. Here's my email address. If you have any questions, feel free to email me. You guys should all have a copy of these slides. Check out the blog. Check out our YouTube channel for some more information on those slides. And Gray, this is your stuff. Did you want to say something?
Yeah, great. Thank you everyone for joining us. Please feel free to check out our calendar of events for upcoming trainings that we might have. Russ, there was a last minute question about oversized systems not working well. Even the smallest mini splits are still too large for most ADUs. So what should be done for these small dwellings? If you have a minute to answer.
Yeah, absolutely. Hi, Julie. Yeah, oversized equipment don't work well, but even the smallest mini split is still too large for most ADUs. What should be done for these small dwellings? And when will they make smaller units? hopefully they do. Yeah, that's actually a really big problem. Pick the smallest piece of equipment you can. If it's a ductless mini split, it's not going to be that big of a deal because it's going to have good airflow because there's no ducts to slow that airflow down. So it will do an okay job, but you're still going to have that same problem of short cycling. But usually in an ADU, and it also depends very much on how good the shell of the house is. The more efficient the shell is, the less likely these problems are going to be. Okay. One of my big complaints about ductless mini splits is that they heat the room they're in really, really well. Well, what about the bedroom over there? The air has to get into that bedroom or the bathroom, let's say, for that bathroom to be warm. If it's a very inefficient house, the heat's going to come out of that bathroom through the window and the doors before the heat from that room makes its way in there. So distribution is to me the biggest problem with ductless mini splits. Now, ducted mini splits, if the equipment is oversized, you want to make sure those ducts are oversized too. You want to make sure that you have really, really good airflow. That will reduce a lot of problems. And then last but not least, variable speed equipment. Okay. There's variable speed, there's 2-speed. You want the equipment to be able to throttle down to match the partial load conditions. So that's probably the most important thing to do. Okay. I really hope they do start making smaller heads for especially the multi-head systems, or even the smaller. I mean, they make window heat pump heating cooling systems that are pretty small. But yeah, you got to do the best you can on some of that stuff because you only have so many choices for equipment. So yeah, good question. All right, that's the last slide there, Gray.
Great. Thank you, Russ. Thank you, everybody, again for joining. I'll be sure to send up all of the follow-up materials from this course this afternoon, and I put my email in the chat if you have any further questions. So thank you all very much, and have a great rest of your day and a good weekend.
There is one last question real quick. It says, what is the proper sequence of the ACCA manuals? It's JSDT. JSD are the main ones. You got to do your load calculations, then you pick your equipment, manual S, and then you size your ducts, and then you design your registers. So it's J, S, D, and then T, if you can do T too. That's it.